for a simple arithmetic logic unit from scratch. Let's think in terms of a verification engineer. What are we given and what we need to do? So we will start with a simple spec. A verification engineer will just be given a spec of the design, and they need to start working on the verification plan and test bench and everything. So let's see the spec and code. So here we have a simple arithmetic and logic unit spec. I just designed this myself, so there may be a few mistakes here and there, but industry wise you will be given a spec something like this with defining all the input outputs and the behavior of the signals and everything. But let's concentrate on this question. We have simple ALU design and we need to write a UVM based test bench to verify the design. Some pointers are given that design is clogged, reset type is active high. When we send the input, the DUT gives the output on the next cycle. Currently, it does not support back-to-back transactions. That's why I just named it ALU version 1.0. Later, we can check for version 2.0. This one supports 4 operations: addition, subtraction, multiplication, division, and also input A should always be greater than or equal to input B. Here are the port names, some properties like what type of ports are they and the size of them. And this is the basic operation that we are going to verify. We have clock, reset, input A, input B, we have ALU select, we have ALU output, we have carry output, and here are the operations that we are gonna check in this DUT. Like ALU select 0 means operation will be A plus B. So we need to design our test bench in a similar way. So let's get started. Um, we as a verification engineer went through the spec, uh, and we can now start from the top module and see what's going on. So this is the platform where we are going to write our test bench. So let's get started. We can start with heading, just some comments. So let's create the top module over here. We can start with just the basic top module. And since this test bench is going to be UVM based, we need to do two things. First, let's just declare the timescale macro. Now, first thing, whenever you start with a UVM test bench, you need to define is um, some UVM base packages. So we need to import them. We do that by writing UVM import UVM package ::star. This is just basic syntax for that. And we also need to include some UVM macros. We do that by this line UVM macros.svh. So this is where we do the declare the basic UVM necessary classes and everything. But we can get started with our top module now. So here we have the space for all the instantiation or sort of include files that we are gonna use. So I'm just giving these headings so that it becomes easier for you guys to later um, make a test bench for your own self. And if you follow these steps, it will become a little easier. So do this. We start with the top module. We keep space for include files, and then we need to do some instantiation. So let's just write it. Instantiation, and then we can start by basic instantiations here. So what we need to instantiate here is some signals that we are going to use, like clock, reset. We also need to instantiate the interface that we are going to use. We also need to instantiate the DUT that we are going to use, and um, we also need to start the test over here. So let's tackle one thing at a time. What we can do is, let's instantiate the DUT first. You can just do ALU and we will name the instance as DUT right now, just for the sake of easiness. And now we need to check the spec, what's the name of all the signals that we are going to use. Though, so according to the spec, if we see, we have clock, then we have reset, then we have input A, we have input B, we have ALU select line, we have ALU output line, we also have carry out. By the way, the names of these signals are case sensitive, so make sure you follow it from the spec word to word. But this is where we instantiate the DUT. We can also instantiate, since our DUT has clock and reset, we can provide the clock from the top module. So let's make a signal clock, and let's also generate the clock to be run across our test bench. So to do that, we just what we do is just generate our own clock. It is not compulsory that you generate same clock as me or same way as me. You can generate it any way you want to, but this is just easier right now because we are going to focus on the test bench and not the clock generation right now. Let's also keep a safety check which terminates our simulation if given number of clock cycles exceeds. So we'll keep it to maybe 5000. We can also display some warning message saying sorry, ran out of clock cycles. And then we use $finish. So what this block will do is, it will run the clock forever. It will keep on toggling every 2 time step, while this will make sure that after 5000 time steps it will call $finish, which will end the simulation so that our simulation does not get hanged. If you want to see the waveforms, you can also use the dump file command to tell the simulator to dump variable values so that you can um, see in the waveforms. So we have this, and we let's see what else do we need. So basic is set up. Now we need to connect the DUT with the interface and then move on with our test bench. So let's create another file named interface, and then create our interface over here. I am assuming that most of you know basics of UVM coding. This video is just to show how can you start coding from scratch, and what steps can you follow to um, bring up your own UVM based test bench. And this should apply to most of the um, most of the spec out there for basic UVM based test bench. So if you just follow these steps, you are good to go. So let's see. Interface will have the same signals as DUT, but the only change is, let's see. So all the signals that are there in the DUT, you also need in the interface. So what we are gonna do is we will just use this for the namesake, and let's see, we will use logic reset. This is just so that I don't forget the names. Interface will have a reset signal, then it will have um, inputs which are 7 down to 0. This size is defined in the spec, so make sure we follow the spec in order to match the exact size. And we say that our inputs are A and B. Then we say that ALU select signal is again 4-bit, so that is all defined in the spec, but we don't want to name it ALU select. Let's name it opcode, operation code, so that it's easier for us to understand. And then we also have ALU output, which is a 8-bit output, so we can name it ALU output, but let's name it result so that it's easier for us. And finally we have carry out, so we will name it carry out. And the signal names are case sensitive, so please make sure you don't make a mistake over there. So now only one thing is remaining is clock. So clock will act as a port. The reason we are defining clock over here is because clock is coming from top module, so we need to define this as a port. So excuse me, what will happen is we generate the clock in the top module and then we pass it to interface and the DUT. So that's why we defined it as input port. So this is our interface, but if we want to use this, we need to include it here. So we do it by include interface.sv file, and then we can instantiate the interface over here with the same name that we used to create the interface. We will call this intf, call this instance intf, and we can connect the clock that is there in the DUT, sorry, in the top module to the interface. So we can say clock. So this clock goes to the interface as well as the DUT. Um, but what we want to do is let's do let's just pass this clock to the interface, and then we'll pass that interface clock to this clock. So to do that, we just connect interface over here with all the signals. So this, we just say interface dot clock will be connected to the clock of DUT. Then we say interface dot reset will be connected to the reset of DUT. Interface dot A, interface dot B, interface dot ALU select, we want to connect it with opcode, so we will say interface dot opcode. Let me make sure if the name is same. Yes. And then ALU output, we want to connect it with interface dot result, and we want to connect carry out with interface dot carry out. Actually, let's do this. So we have connected the interface and DUT, and we have clock. We also have dump file and um, a safety check for limited number of clocks. So we can move on to next module. Okay, let's now proceed with the test class. Let's create a new class named test.sv, and we can start with naming our class ALU test extends UVM test and class ALU test. So first thing we need to do in a class is declare the necessary macros that will help it register everything with the UVM classes. So we need to call this macro called UVM component utils, and we need to pass the same name of the class that we are going to use. Now, first thing we need to do is write a constructor. So let's see, function new and function for a component. Since we have used UVM component utils, ALU test is a component. So we need to pass two parameters with this string name is equal to the name of the class, and then we also need to write component parent. So we also need to call super.new, so we'll write this by super.new name comma parent. We are just passing this name over here and this parent over here. So this is just a basic syntax for a constructor in UVM classes. If you want to read about it more, like why do we use UVM component parent, you can find some documentation on it. But let's not get into it right now because it will take a lot of time to write this test bench. So um, if you have more questions about it, you can just comment or contact me on LinkedIn about it, and we can definitely discuss that. But let's move on. So we just use the constructor. Let's also keep some display statements so that it becomes easier for us to debug. We will use the default UVM info macro that UVM already has. We can just write, it has like three parameters. First is the tag of the comment that we want to give. We can just give test class And then we can also use just some comment that we want to pass, like inside constructor, and then verbosity level. We will just keep this UVM high, and later in later videos I'll explain why I kept this, but it has to do with different verbosity level. Like some messages might be more important for you than others, so this will help us in later stage. But since this message might not be as important, I'm just keeping it as UVM high. I'll explain about it later in later video, but you can also just search for UVM verbosity and you'll understand what's it all about. So we are done with the constructor, but now we need to write the build phase. So we do that by function void build phase and function same. Here also we need to call the super method, which will call the parent build phase method. It's all just part of UVM classes. We also need to pass object handle of UVM phase, and let's also write a display statement over here as well. We can just write build phase. Now let's write for connect phase, which is similar to build phase, but we'll just change the syntax. Connect phase. I'm just trying to save as much time as possible. Connect phase. And then we also need to write run phase. There are a lot of phases in UVM, but these three are the main phases that we are going to use: build phase, connect phase, and run phase. Maybe in later videos we can see um, about other phases, but uh, these are the basic phases with which our ALU could be verified easily. So let's see. All the other phases are functions, while only the run phase is a task, because run phase can consume time and it can have time consuming statements, so it needs to be task, whereas functions cannot uh, include any time consuming statements. So this is a very good interview question. Same syntax as above: UVM phase, and then you can just write your logic over here, run phase logic. And this is just a basic container of ALU test. All our classes will have similar container for a component class. So what I'll do is just copy this as a template, so that all the other class we can just copy it from here. I suggest you write every class from scratch, but to save time in this video I'll show you. um, I'll just copy this for other classes like environment, driver, agent, monitor, etc. So let's see. So for verification of ALU, what uh, we need to think about is the architecture. So we decided that our architecture will contain a top module and then classes will be test class, environment class, agent class. There would be one scoreboard, one interface. Agent class will contain driver, monitor, and sequencer, and then we can add the sequences and sequence item. I will link the block diagram in the comments below, so that it becomes easier for you to view. But let's create the environment class, which will be same as the test class. So let's see, in env.sv, I'm just copying it. Let's copy from the template. I'll just copy it over here. We want to name it as ALU env. We'll just replace wherever we have ALU test, and here in the comment we will just write env class. The reason I'm copy pasting is to show you that uh, classes are reusable. That is the whole point of universal verification methodology, that we can create such classes that most of the parts of it are reusable by other classes, or even other test benches. So this, we have env class. Now let's also create a agent class, driver class, monitor class, sequencer. So let's first create agent.sv. We'll just copy it from here. One more thing is ALU env will extend from UVM env. It won't matter a lot even if you keep UVM test, because most of the classes are extended from component class, but there might be some features that are declared in UVM env class that we might want to use in future, so it's better if we just use this. This is just a concept of inheritance, um, so which is very important for a verification engineer to know. So if you guys don't know about object-oriented programming, I would suggest you first um, learn more about 4 pillars of object-oriented programming, and then this should be very easy. Anyways, let's get started with ALU agent, which will extend UVM agent. And let's just replace the names. Agent class. Now let's do that same for driver class. Now agent will have 3 classes: driver, sequencer, and monitor. So let's create driver class first. Will same name as ALU driver. We'll rename it here as well. So same as that. Now let's also create monitor class and sequencer class just like this. I'll just quickly skip to that part. So I have the monitor class and sequencer class, and the driver class. Just a few things to note here is the driver class is a parameterized class, so we need to um, pass the name of the sequence item class that we are going to use. We haven't created the sequence item class, but I know the name of it will be sequence item, and same for the sequencer class. We need to pass the parameter over here so that the driver knows what type of sequence item that we are going to drive on the sequencer and driver. That is why we pass this as a parameter to let it know the type of sequence item that we are going to use. Also in the sequencer, we don't need the run phase, so I'll just skip that part. Actually, we are not going to use any phases in sequencer, but just since this is a basic test bench, I'll just let it be so that you guys understand what's going on in the sequencer. Now let's declare our um, sequence item class and sequence class. So let's define sequence item.sv, and this will be our sequence item class. So since this is an object class and not a component class, I won't copy everything from the template that we had. So we will just write class ALU sequence item extends UVM sequence item and class, just copying the name. And just like the component class, this class will also need a macro, but it will be UVM object class. I'm sorry, UVM object utils, and then the same name. We can instantiate some variables that we are going to use, and we also need to define the constructor. So let's see, constructor for an object class will be defined in this way: new, and in object class we just pass the name, which can be done something like this: super dot new name, and this is our sequence item class. Here we can just define some the signals that we are going to use, reset inputs and outputs. So to do that, we just go to the interface, we copy this, and we can paste it over here. So now since this is a sequence item class, what we are going to use this for is to generate random values about input and input values, and to store the output result. So to do that, what we are going to do is declare these signals as rand signals, which means they will be randomized when we just call randomize function. So we just add the rand keyword over here for the opcode as well. The result is result part is output, so it, like, we don't randomize the output, of course. Carry out is also an output, so we don't randomize them. Let's just write it here so that we remember. This is our sequence item class. Now let's write a base sequence. We can say sequence.sv. Sorry about my keyboard because My other keyboard was making noises in this mic, so I decided to use a different one which I am not used to. Anyway, this is also an object class, so we will write class, and let's give this as ALU base sequence extends UVM sequence and class UVM object utils the name and constructor function new. Let's give a basic display statement over here so that we know when our sequence is constructed. We can say base sequence and just say inside constructor. Or let's write UVM high here. So there are different, like we can also use UVM low, UVM medium, UVM high, UVM full, UVM debug, but that's for later use. In sequence class, we need to define body, like what is going to happen when we call this sequence. So we do that in the body class, sorry, body task. And let's also print base sequence. This will help in our debug inside body task. So this is how our sequence item sequence class will look like. We can let's after creating this, let's also declare these in the test in the top module. So let's first delete the template, we don't need that. Here let's include the classes. The way we include the classes, the order of the classes is very important, because um, the first class that you are going to use should be the first one, and so on. So we start with sequence item class, and so on, so that it does not give us the compile error. So now we have included everything. Just one thing we need to do in our top module is start the test. So to do that, we just write initial begin, and we call the run test task in the top module. This should take care of our test. So when you reach this stage, our basic architecture has been defined, like containers have been defined, but we do need to write some logic of what's going to happen. But what you guys can do is just simulate this much so that you can find out if there are any major compile errors. If so, you can solve them. If not, we can move ahead. So I have a compile error saying I don't have a scoreboard.sv. So we, of course, we do need to include the scoreboard, but we'll come back to that later. Scoreboard.sv, we will just create the file and then compile and see if everything looks okay. So let's see. Okay, my compilation is successful, which means I don't have any errors in these files. So we can move ahead with our main logic now. So now let's move on to the next step, which is once we have all the components, first thing we can do is set this interface so that it is available in every component. So to do that, the reason we are doing that is interface is a physical entity which we cannot instantiate in dynamic entities like classes. So we need to pass a handle to that interface. So to do that, what we will do is we will set the interface somewhere in the top module, and then we in the test bench we will get that interface handle. So to do this, we just write we use the UVM Config DB method to set the interface. The syntax is something like UVM Config DB, and then we pass the type of interface, which is virtual, and the interface class name, and then we call the set method, which takes 4 arguments. If it gets a little complicated, you can just remember that it takes 4 arguments, which is null. Then we say star. I'll explain in a minute what it means. The first parameter plus the second parameter will specify the path where this handle will be available, so that those paths can be able to access the interface. So that is the path, and then we want to name that handle intf, or we can name it, let's name it VIF, virtual interface, and then we can set the object handle name as VIF. So what this means is in the config DB we have a handle um, VIF which can be accessed through name VIF, and which is available for every component. Star means every component to access that. We can also specify a specific path, like we can also make it just available to the test component or just the environment component, but we that's a little advanced and we don't need to get into that right now. So here we just set the virtual interface. Now which are the components that will require the virtual interface handle? Those are the driver, monitor. So what we can do is we can directly get the interface in the driver and monitor. The best or the better way to do that is to get it in the test component and then pass it in the environment component and then in the agent component. But let's keep this simple for now and just pass it in the driver class. So let's go to the driver class. Also, if you noticed, I just added some comments like this so that it becomes quite easier for you guys to read through the code. So in the top module we just set the interface. Now we need to get the interface, so we can get that interface in any function that we want to, but ideal way is to get it in the build phase. So let's go to the build phase of driver class, and here we will get the interface. The syntax to get the interface is same: UVM config DB, type of the interface virtual ALU interface, and instead of set we use the get method. Get method also takes four I'm sorry get method also takes 4 arguments, First is the class that is requesting. So first plus second makes the path of the class that is requesting the virtual interface handle, and then the name that we set for that handle, which is VIF. And now when we access that VIF from the config DB, we want to um, copy or sort of use a name that we can use throughout the driver for that class. So what name we want is we can use VIF driver. So we do need a handle for this, so we do need to declare it in the class somewhere here. So what we declare is virtual ALU interface, and the handle would be VIF driver, so that we know that this is virtual interface inside the driver. But let's keep things easy for easy here. Let's just keep it VIF for now so that it is universal. And one more thing is we are calling this get method, but what if this get fails and it does not get the it is not able to get the interface handle? What should we do then? So let's keep a safety check over here. What we can do is we can say that if I don't get the virtual interface, so if I cannot access or get the handle for interface in the config DB, then please throw me an error. So we will say that UVM error, and then we just give a tag to that error. We say that hey, this is from driver class, and the message that we want to print is failed to get VIF from config DB. That's it. UVM error macro takes just two um, arguments. So this method actually returns 1 if it is able to get the interface, and 0 if it is not able to get the interface. So we are just checking that hey, if it does not return anything, which means we are not able to get the virtual interface, that means please throw an error so that I know that driver did not get the interface handle. Same thing for monitor. So let me just copy this. We go to the monitor build phase and just paste that, but we also need to instantiate the interface and this. So let's also copy this and change this to monitor class so that we know from the tag. At this stage I would recommend you guys to compile everything and see if virtual interface is able to um, use the set and get method inside your test bench. If it does, well and good. If not, it's better to debug right now rather than at later stage. I did get some error. Let's see. I got an error saying I cannot use this. That is correct. So why am I not able to? So the set method passes the handle inside the config DB, but we don't have handle any handle named VIF. Our handle name is INTF, so we need to write INTF over here and save and then run it. Now we need to do is start a basic sequence. So let's see if our sequence class is ready or not. we have a sequence item class. So let's just give a finish over here, and let's see sequence if we need to do anything. So the sequence will start or generate a sequence item class packets and then send it to driver. So in order to do that, we need to instantiate the sequence item class over here. We can say um, base, or let's call it reset packet, and then we need to send it to the driver. So the syntax for that in the body task is something like, first we need to create the packet for this. So we say reset packet is equal to sequence item. We call the create method, type id create, and we say that name of our packet is reset packet. You can give any name here you want to, but I generally try to give the same name as the handle name so that I can easily debug. So once we create, we need to start item and finish item, and we need to start and finish this packet for the driver. What we need to do is, when sequence calls this start item, it will get a lock or sort of permission from sequencer that hey, you can start your sequence in the driver. And after that, what we want to do is we want to randomize that package. So we call packet.randomize, and we can say, since this is a reset package, we will set the constraint to be uh, reset equals to 1, so that we are just, this sequence will just reset the DUT that we have. So oops, so this should be our reset sequence. We can also create another sequence which is not reset sequence. So let's go ahead and create that, or actually let me type it for you guys. Class ALU test sequence extends. Now let's extend it from our own sequence, because we can just use our it becomes more reusable in future if we want to include everything in the base sequence. So we use this end class test sequence, and rest everything is almost same as above, but just one thing is we need to make sure we change the names, and also this is test sequence. So in the test sequence, let's give this a name as maybe just item, and we also rename everything here. Start item, um, item dot randomize. But now let's do it with randomize reset is equal to 0, because now with this sequence we don't want to reset anything. We want to drive some values. So let's do this. So our basic sequence is ready. Let's see if our sequence item needs anything. Let's put some default constraints that we want in our sequence item. So default constraints. The constraints here will be defined from the spec. So if we look at the spec right now, Let's see. So from the spec, if we see, we have a couple of constraints that we need to um, add. One is it does not support back-to-back transactions, which means we cannot drive the sequences back-to-back. We need to give some kind of delay between that. So we need to take care of that. Second is it only has 4 operations right now: addition, subtraction, multiplication, division. This is very important because our ALU select is 4 bits. So possible values are 2 raised to 4, but we are only going to use 0, 1, 2, and 3. Rest other values are reserved right now. So what we need to do is constrain our ALU select value to be inside 0, 1, 2, and 3. It cannot assume any other value, otherwise our test bench will be wrong. So we need to take care of that, and we also need to add a constraint such that input A is always greater or equal to input B. So let's see how can we do that. So default constraint is let's put a constraint for inputs. So whatever constraint I add, you can give name of the constraint anything you want to, but I add underscore C over here to specify that it is a constraint name. This is widely used in industry, so it will be great if you can learn this. So what we need to give is input A and B, where A is always greater than B. So for our easiness, let's say that A inside, let's see, A inside, we'll just use the inside keyword. We can say let's keep it from 10 to 20. Constraint input 1, we can say input 2, B inside 0 to, or let's keep it 1 to 10. So that was the last condition for input A should be greater than B. Now let's also constrain our operation code opcode, because we only need to possible values are 2 raised to 4, but we only need 0, 1, 2, and 3. So we say opcode variable should be inside 0 to 3, or you can also specify something like this: 0, 1, 2, 3. Of course, this is a very basic level of constraints. I'm just keeping it so that it's easier for you guys right now, but we'll modify it later in the test bench. So we have our sequence item and sequence is ready. We have 2 sequences. So now let's also finish other classes. What we need to do is, according to our block diagram, the test component will contain environment class. Environment class will contain agent. Agent will contain driver, monitor, and sequencer. So we need to write the code accordingly. So let's instantiate the environment uh, class inside the test. To do that, we just write environment class name, which is ALUENV, and we will call it ENV class. And this is just instantiation. We also need to create that class. So we do that in the build phase, which is env is equal to ALUENV. We use the type ID create method. And since this is a component class, we need to pass 2 parameters over here. One is the env name itself. So whatever we want the env to be called, to be known as in the test bench, and we also need to pass this as a parameter. This will specify who is the parent of environment. So it's just like ALU test contains environment class. So this is the syntax for that. Let's do same for environment class. In the environment class will contain the agent class. So we say that ALU agent, same way we create in the build phase. Similarly, agent class will have driver, monitor, and sequencer. So let's do that as well. Now, once we are done with the build phases, we will move on to connect phase. But we need to make sure that the flow, architectural flow is correct. We have our test class, it will construct environment class further will construct agent class, agent will further construct the driver, monitor, sequencer, and we are good to go. We'll come on to the scoreboard later, but let's see this. Now we need to see what we need to do in the connect phase. So connect phase, we will just connect. What we need to do is connect monitor with scoreboard over here. Now let's move on to the run phase of each components. What each component does is, I'm assuming that you guys already know the basics of test bench. So let's see the run phase of test class, what it does. Test class should, what it does is it will start the sequences that it wants to run. So to do that, one important thing test class we need to do in test class is we need to say that, hey, I'm going to run my uh, test here. So what I need to do is raise an objection so that it knows um that we are running our sequences. To do that, we use the phase dot raise objection, and we also need to, after we are done with the test, we also need to drop the objection so that the test can end now. And we need to pass, the syntax is something like this, and here we can start our sequences. So in order to start our sequences, we need the sequences instances, right? So we have two sequences that we created. One is the base sequence and another one is the test sequence. So let's just create handles for that. We say that test sequence and base sequence. We can call it reset sequence, and this one we can call sequence 1, or we can, let's call it test sequence. And now let's just start the reset sequence first. So we can do that by, first we need to construct the reset sequence by using the type id create method. So we just do that. After constructing, we need to start that sequence. So how are we going to start that? Is by saying that, hey, start my reset sequence on what? So we call the start method, which is predefined. We say that, hey, start my reset sequence on sequencer, which is path of that sequencer is something like env agent sequencer. Because our sequencer is lying inside the agent which is lying inside the environment, so we specify that path over here. So this will, what this will do is it will start this reset sequence on this sequencer which is lying inside this agent, which is in turn lying inside this environment, because there can be multiple environments and multiple agents and also multiple sequencers. So we are specifying which sequencer we want to run our sequence on. So that was the reset sequence. Let's see the test sequence now. We can just write same thing we need to do. So let's start the test sequence, which we can do is similar in as reset sequence. And we will say that start this sequence on the same sequencer. So we just say, sorry, we just start this sequence and looks like we are good to go. So this was the test class, the run phase of test class. Let's also see what uh, other classes need in order for us to run a demo test right now. So one thing we need to do in agent class is in the connect phase we need to connect the um, sequence item ports of driver and sequencer for it to exchange the transactions. So in the connect phase we just say that driver dot sequence item port, sorry, port dot connect, and where do we want it want to connect it is we want to connect it to sequencers sequence item export. These are the ports that are by default defined inside the driver and sequencer class. So this is how we just connect them. They are used to exchange transactions between sequencer and driver. So we are just making sure in connect phase we have a handshake between our sequencer and driver. Now let's move on to the run phase of the driver, which is the most important sort of phase in the driver. So one thing we need to do first is declare the handle to the item that we are going to use, which is ALU sequence item. So we are going to use this in driver. What does driver do is drive the logic that we want to use to simulate the DUT, and our DUT is ALU Testbench. ALU DUT, which takes two inputs and gives out the output based on the operation code. So let's just drive the inputs to the interface with this handle. So in order to do that, we just what we do is, first of all, let me uh, give UVM info over here so that we don't like we can easily debug that. Then what we want to do is forever run this driver task until the simulation ends, like forever keep driving this transactions. So this is the syntax for that. And then what do we want to drive? We want to drive this packet. which is called item. So item, first we use type id create method to create it. So we just write item and call the type id create method. I'll just skip to the end, and then we use the ports that we declared in the agent. So we just use this port inside the driver to get the sequences from the sequencer. And to do that, we use this method get next item, and we get that item inside this item class that we created here. And then after doing or driving something, we can just call sequence item port dot item done, indicating that we are done driving the item and we are ready to move on to get next item. So the logic over here is um, simple. We can just create a task that can drive the items. um, it's not necessary to create this task. You can just easily write down here whatever the logic is, but this is a um, easy way, so that in case you need to change something in driver class or drive method, it does not affect the run phase, because it's the most important phase. So let's define the drive task. I'll just give this heading task drive and task, and it also has, we are using the item here. This is, since this is object, it is passed by reference. If you don't know the meaning to that, please um, refer to some online data or just contact me on LinkedIn, and we can talk more about pass by value and pass by reference in a task or a function. But let's see, we have a drive task over here, and we want to drive the packet transaction on the interface, but we want to do it only on posage of clock. So posage of clock, but where is that clock? Where can we access that clock? We can access that clock from virtual interface handle that we already have. So oops, vif.clock, and then we want to drive all the inputs to the interface. So we just say that interface dot reset and we use non-blocking assignment over here, because it is better to use non-blocking in a driver. It's not necessary though. Interface dot a will be assigned item dot a, same for interface dot b item dot b, item dot opcode. So the logic is quite simple. We are just driving the item or the packet class values in the interface class. That's it. And similar thing we need to do in the monitor class. This is, we are driving on the interface, and in the monitor class we are sampling from the interface. So let's see how would that look. We can go to the monitor class, and same thing here. Also we will need name of the or handle to the item class that we are going to use. We can name this any name you want to, but let's keep it item for simplicity. Now let's go to the run task. Let's also add UVM info over here so that it becomes easier. Then same here as well, we will write forever begin block, so that we keep monitoring until our simulation ends. So here also we need to create the item class. For that we use the same type id create method. Now in monitor, what we want to do is we want to sample the inputs, then we want to sample the output. So in order to do that, first thing we need to do is um, what we will do is we'll go to the interface and see what signals do we have. We have reset and everything, a b opcode result carry out and clock. So first thing we need to do is make sure that our monitor only samples when it is not reset, because we don't know how the DUT behaves when it is in a reset mode. So we say that, hey, wait until it is not until it is not in reset mode. And oh, I know what mistake I made over here. Since we are not using INTF, we are using VIF. So we need to declare this as virtual interface. Oh, sorry, we need to use it as the same handle that we used over here. It doesn't matter the name you give, but this is just easier to remember. So similarly here, we won't use INTF, we will just use VIF dot reset. So this will make sure that it will keep on waiting over here until the DUT is not in reset mode. Then we want to sample the inputs, but we only want to sample the inputs on pausage of clock. So we do that by, sorry, one more thing. Okay, just making sure. So we do that by writing at pausage of clock. We want to sample we want to sample A, B, and opcode from the interface. So we say that, hey, sample the interface A and copy that value to item.a. Similarly, we want to sample B. Here I am using blocking because it is a general practice to use non-blocking for driver and blocking for monitor class. But if you use otherwise, that is also completely fine. We have opcode, then we have opcode as well. This is how we sample the inputs. Now we also need to sample the output. And if we look at the spec again, we had one caveat. The caveat is when we send the input on current cycle, the DUT will give output on next cycle. So now we want to wait for one more cycle, one more pausage of clock. So to do that, we will again write at pausage of clock, and then we will sample the output, and output we call it result. So this is how we will sample the output. Now general flow would be to send this packet to the scoreboard, but let's first um, see if everything is looks correct. Let's try to simulate this and see if there are no syntax errors at this moment. I got some typing errors, which is, of course, I have some typos, of course. Let's see this. Sorry about that. My keyboard is a little new for me. Oh, one more typo, which is raise objection, and we have drop objection over here. Oh, one more mistake. This is of type test sequence and not base sequence. Looks like we don't have any compile issues, but let's also start the test. Till now we are just checking compile issues, but we need to start the test. To do that, we need to pass our test name inside this. So our test name is ALU test. We can also pass this from a parameter of through command line, but let's just put the test name over here. And uh, I would suggest you guys to run your test till this much, so that you know if there are any mistakes, you can solve it right now rather than scratching your head after making the design, the test bench complicated. So now let's code the scoreboard. What scoreboard does is, what we are doing is, from the driver we are driving the transactions one by one on the interface. The monitor will sample those um, inputs, and then scoreboard will compare uh, if the result that we expect versus the result that is actual from the DUT is correct or not. So from the monitor we will send this packet to the scoreboard, but let's get the code for scoreboard ready first. Scoreboard is also same as any other component class, so I'll just copy this, and sorry about that, I'll just quickly remove unwanted things. Let's rename our scoreboard class ALU scoreboard, and let's call this SCB class. So this is our scoreboard class. It should be similar. Now one thing we need to see is how are we going to connect the scoreboard and monitor. So just like how we connected the driver and sequencer through these ports, sequence item port, sequence item export, we need to connect monitor and scoreboard. But fortunately for us, the driver and sequencer had these ports by default, but monitor and scoreboard does not have them, so we need to create those ports. So let's create those ports. We will create analysis ports. To do that, we just go to the monitor, and the syntax is something like UVM analysis port. We pass the parameter, we say that what kind of sequence item are we going to drive through these ports. So we say that we are going to drive packet of type ALU sequence item, and then we can name the port as, let's name it monitor port. And then we also need to create this, just like the type id create method, we can just use the new method for this port. So we can do this in constructor as well as the build phase. So it's not gonna make any difference, but let's do it in the build phase. So we say monitor port is equal to new, and we need to pass two arguments. First is the name of the port, and second is the parent. Similarly, we need to do this for scoreboard port. Now the caveat is this is the port which is so from this port we will be sending packets to the scoreboard. So scoreboard port will be a receiver port, whereas this is a transmitter port. So receiver port um, looks like, or we call the receiver port as UVM analysis IMP. IMP means implementation port, where the what needs to be done from the packet that we send from the monitor. The logic is defined in this class. So we say that UVM analysis IMP, and we have to pass two parameters over here. One is the sequence item name that we are going to use, which is, or the sequence item type that we are going to use in the scoreboard, which is this, and the name of the scoreboard. Now we can call this port as scoreboard port, and same thing, sorry about the spelling mistake. Same thing we can do, either construct the port in constructor or the build phase. Let's do it in build phase. Scoreboard port, we say that sorry, new, and then this and the name of the port. So we finally constructed two ports, one in monitor and one in scoreboard. Now let's connect them. So in order to connect them, we will always go to a higher component than these. So agent and scoreboard lie on the same hierarchy, while driver and monitor and sequencer lie inside the agent. So now we need to go a hierarchy above agent and scoreboard, which is environment. So when we go to the environment, we can connect those ports in the connect phase. We just write monitor dot connect scoreboard. So but we don't have the monitor handle over here, right? We need to access it through agent. So agent dot monitor dot monitor port dot connect with what? We need to connect it with scoreboard. But did we instantiate the scoreboard? Not yet. So first we need to do is instantiate the scoreboard inside the environment, just like the agent. So now we know that agent and scoreboard lies on the same hierarchy. So let's do this, and also use this type id create method to create the scoreboard. Now we can use this handle to connect scoreboard port, and this is how we connect monitor port and scoreboard port. Now the important part is okay, our driver is driving the items, our monitor will monitor the items or sample the items, and it will then send to somewhere here. We will send item to scoreboard through the port, and scoreboard will do something with it. So first thing, let's try to send that to the scoreboard. To do that, we just write monitor port. We use the monitor port dot write. What do we want to write? Sorry about typo, I hate my keyboard. We use monitor port dot write item, so that we are just writing this item inside the monitor port. But we also need to implement this write method inside the scoreboard. So to do that, we will just do something like this is the most important part of the scoreboard, write method. This determines what is going to happen when monitor sends the item in the scoreboard, which means we are implementing this method here. Implementing, that's why the name over here, the port name is UVM analysis implementation port, because we are implementing this write method over here. Write method is always a function, so watch out for that. Function void write end function, and we also need to pass item as a parameter. And now what needs to be done over here is, let's say monitor sends or writes this item in the port and scoreboard will receive it. So what we need to do is make a database or store that item or packets. Let's say there are, maybe we run the sequence 100 times and we want to save all those 100 transactions. So we can use a data structure to save those all the packets. Easiest data structure is the queue that we can use, so that it becomes a sort of a FIFO order, first in first out order, that we can use. So let's create a queue first. Queue should be of type sequence item, and we can call this queue as transactions, and let's use this transactions dot push back. What do we want to push is this item. So one by one we are just whenever this method will be called, we are just pushing this item into transactions queue inside the scoreboard, so that we have this transaction queue. Now in the run phase we will do something about those transactions, maybe compare or something like that. So let's see what we need to do in the run phase. In the run phase, same way for other run task, other run phases, we just want to keep on uh, running this forever until the simulation ends. And what we want to do here is the flow will be something like get the packet, generate expected value, and then compare it with actual value, and then score the transactions accordingly. So let's see, first thing we need to do is get the packet. How do we do that is, we already have this queue transaction, right? um, so the easier way would be just copy the packet from this over here in the run phase. So just let's just do this, and we can call this current transaction, and here we need to wait for um, until the transaction queue size becomes greater than 0, right? We don't want to run this task if we have not received any transactions. So we need to wait for receiving until we receive a transaction. So to do that, we just say that wait for transactions dot size not equal to 0. So non-zero queue size will uh, non-zero queue size means we have some transactions. So that, so once we get the transactions, what we need to do is we just copy that, um, copy only one transaction at a time, and then we play with that in the forever loop. So let's copy that first in this handle name current transaction. So current transaction is equal to the transaction queue dot pop front. As I said, it should behave like a FIFO, first in first out. So you should play with your transaction which you received first, and then in that order. You don't want to juggle the order of that transaction. So we do this. Now we have, let's say, the first transaction in this handle, right? And we want to uh, do something about it. We want to generate expected value and then compare it with actual value, and then score the transaction accordingly. So maybe let's break it down into another uh, task. Let's call it maybe compare task, and we just pass this handle in the compare task. You can call it any name you want to. So let's create another um, function or a task. We can call it compare end task. I'll just give some comments over here so that it's easier. Also, since we are passing this, we also will need um, this over here. Now what we need to do is, first of all, generate expected value and then compare it with actual value. So let's define two variables called uh, expected and actual. Actually, let's keep this type same as that of the result. So let's keep it logic 7 down to 0. Actual and expected. Now let's generate the expected value. So expected value, to generate the expected value, we need to look at the spec. As you can see in the spec, when we will have to write a case statement saying that when we have ALU select value 0, or in our case operation code opcode value to be 0, we have a plus b. So our expected value will be a plus b, or if it is 1, our expected value will be a minus b. So let's write a case statement for that. So we write case and case, and we want to check the opcode. So if the opcode is 0, what should we do? Opcode 0 means a plus b. So our expected result will be a plus b. So a plus b from the packet that we sent from the monitor. So monitor will sample the a and b and then send it to scoreboard, and here we will add those values. So this plus that same packet b, or if the opcode is 1, the result should be a minus b. So expected value becomes a minus b. Or if it is 2, the result is a multiplied by b. And if it is 3, the result is a divided by b. So this is how we will generate the expected value. Now let's just copy the actual value. Actual value will be just simply the result that we sampled from the DUT. So that is what we sampled over here in the monitor. We sampled the result and we sent that in the packet, and we are just copying that in the actual variable. So now we have this. Now we can just say that last thing we want to do is compare it with actual value and then keep a score of it. So let's compare. How do we do that? It's just simply if condition. If actual is not equal to expected, then we want to throw an error. We say UVM error and we can just give tag as compare and say that um, so here we will use this factory function called $s format f just to print values and string that we want that we require. So the syntax is something like this: transaction failed actual is equal to this, while expected is equal to this, and we want to print expected and actual. Else we want to print info statement saying that transaction was successful. This is not necessary, just that it will look beautiful when we see the transactions passing. Let's also use same $s format f. Just that here we can say transactions passed, actual and expected, and the syntax for UVM info requires one more argument, which is the verbosity. Now let's keep the verbosity to low, which means it will print regardless. um, we'll get back to the verbosities later, but this is a very important statement that we want to print, so we will keep it as UVM low here. And let's see, is there anything else we need to do? Just finish this. Looks all right. So from the monitor it will write it in the scoreboard, and scoreboard will um, keep all the transactions, and one by one it will keep compare and keep score of it. So let's run it and see if we get any errors. So after doing this, just run it for once and you should see um, your transactions passing. In the next video I'll show what I see in the simulation. You can of course check out the same code in the link mentioned below on EDA Playground. But one thing I wanted to mention is in the test class, let's just uh, repeat this sequence for maybe 100 times and see, and you can see the 100 transactions passing. The only thing I wanted to mention here is I am adding this extra delay because our spec clearly mentioned that we are not, the back-to-back transactions are not supported. So once we send a sequence, we need to wait for some time. That some time is just arbitrary right now, so I'm just using 10 as the value, but you can use any value right now depending on the spec. So finally you can just run this and you'll be able to see the display values. In the next video I'll show you what I see in the when I simulate this. Hopefully this video was quite helpful for you guys. See you in the next video. Bye.